All right, here's some additional problems for you for Unit 7. Two beads are fixed to a rod that's rotating at a constant speed like this. Which bead has the greater speed? Well, B has a greater speed because in the same amount of time, this bead is going to get to here, and this one's going to get to here, and this one has to cover a greater distance in the same amount of time because the rod's going to get there, of course, just at one time. So B, greater distance in the same amount of time. Which bead has the greater centripetal acceleration? Well, let's see. That acceleration is equal to v squared over r. So the speed of this one depends on, would be like 2 pi r over t, right? So I'd have the speed of, well, let's say the centripetal acceleration of the second one is equal to 2 pi times the radius where b is over time. That's its velocity. Right, this is how, sorry, let me write the equations down here that we know. We know that centripetal force, that the unbalanced force when you're moving in a circle is mv squared over r. Force is mass times acceleration, so acceleration is v squared over r. And we also know that the speed of something moving in a circle is 2 pi r over t. Might need the friction equation. We'll throw that into the mix later when we need it. So this is my v, 2 pi times the radius of this one over t. That's my v squared over r. And then the acceleration for a, for this one, is the same thing, 2 pi times the radius at a squared over t. And the time period for them is the same because they're attached to the same rod over r a. Now, all of this stuff, 2 pi, constant, this is the same for both. The only thing that matters is the RAs. Those are the things that are changing. I have on the top of this fraction RB squared over RB, so the acceleration is directly proportional to the radius. And since RB is bigger than RA, which one has the greater? RB does, or particle B does. Because math, right? Because of this. Like this whole thing just simplifies to a number times RB, and this turns into the same exact number times RA. So that means if RB is bigger, the radius at B, then that's going to be a bigger acceleration. A 615 kilogram race car completes one lap at a constant speed in this much time around a circular track with a radius of 50. So what's its speed? It's 2 pi r divided by the time. Right? 2 pi r divided by the amount of time it takes to get around that track one time. So let me do that real quick in my calculator. 2 pi times 50 divided by 14.3, and that's about 22 meters per second. All right. Calculate the acceleration of the car. So the centripetal acceleration is v squared over r, and that's 22 squared over the radius of the track is 50. About 9.7. Calculate the force the track must exert on the car to allow the car to travel in a circle. Well, that's just the unbalanced force that we know we need to have if we're moving in a circle. And I already have this part of it, so I could do mv squared over r, but this is the v squared over r, right? So I just need to multiply this by the mass of the car. And that's it. That's about, let's see what I want to round that to. If we did 2 sig figs, I guess it would be like 6,000. I guess I'm going to call it 5970, 5,970 newtons. I don't care exactly how you round, just don't give me too many decimals. All right, calculate the maximum speed a car can successfully complete an 80-meter radius turn on a flat road if the coefficient of friction is 0.4. So we have seen this exact problem before. The unbalanced force on the car, let's say this is the center of the turn and it's like driving straight at us, like around the turn, kind of like this. Then force of gravity, normal force, those are equal in this case because there's the center of the circle is not up here or down here, it's over here. So the force of friction is the thing that's pointing toward the center of the circle. So that unbalanced force toward the center has to be equal to the force of friction. And this is mv squared over r. And this is equal to, how do you find the force of friction? Force of friction is equal to the normal force, mu times the normal force. How do you find the normal force? It's the same as the force of gravity. How do you find the force of gravity? It's equal to 10 times the mass of the car. So if you're thinking that the mass of the car is missing here, you don't actually need it. It cancels out. It's going to show up on both sides of this equation. Of course, if that happens, you could just, if it really doesn't matter, you could make up whatever mass you want for the car, and it will still, the math will still work out. All right, so mu times the normal force, that's mu times the normal force, which is 10 times the mass of the car. So the mass of car cancels out. And what are we trying to find? We're trying to solve for the maximum speed. So v squared would be equal to mu times 10 times r. So the square root of that is what I need. I need about 18 meters per second. All right. Number 4, according to the 1990 Guinness Book of World Records, highest rotary speed ever attained was 2,010 meters per second. It's about 4,000 miles an hour. The rotating rod was this long. Assume that the speed quoted is that of the end of the rod. So calculate centripetal acceleration from the end of the rod. So centripetal acceleration is equal to v squared over r. Now if this thing's rotating like this, then the radius here is, if this is how long the rod is, the radius is actually half of that. So I think that's maybe a little bit tricky. And we also need to change that from centimeters to meters. So the radius is 0.0765 meters, half of that, and then converted to meters. So v squared is 2010 squared over 0.0765. And that is a lot of newtons, a lot of meters per second squared, rather. That's about 3,000, if I rounded to 2 sig figs, about 310,000 meters per second squared. That's a lot. If you were to attach a 1 gram object to the end of the rod, how much force would be needed? So this is the acceleration. You could do unbalanced forces, mv squared over r. This is the v squared over r right here. So that would just be the mass, 1 gram, that's that many kilograms, times the 310,000. That's going to move the decimal place 1, 2, 3. So 310 newtons of force. Yowza. A carnival clown rides a motorcycle down a ramp and around a loop-the-loop. If the loop has a radius of 18 meters, what's the slowest speed that the rider can have at the top of the loop without falling off the track? Okay, I'm going to tell you something here in case we didn't run across this somewhere. As you go through this loop, the slowest speed is where the normal force backs off to 0. The slowest force means that the normal force has backed off to 0. And then as soon as you get through that spot, you're going to start pushing against the track again. If you go any slower, there would need to be like negative normal force on you. In other words, the track would need to be pulling up on you, and it's not going to because it can't. So that's when you start to fall out of the loop. So normal force is 0. That's the boundary condition for barely making it through the loop. Now, if we made a force diagram here, we'd have, of course, the force of gravity, and then if the normal force pushing down on the person has backed off to 0, then this is the only thing. So it's actually a real easy problem once you realize that the unbalanced force toward the center of the circle is only the force of gravity because the normal force is backed off to 0. So that's mv squared over r is equal to the force of gravity is 10 times m. And like number 3, we don't actually need to know the mass because that cancels out. And we want the slowest speed, so v squared is going to be equal to 10 times, multiply that up to the other side, so whatever the square root of 180 is. So that is the slowest speed you can make it through the loop at. 75-kilogram pilot flies a plane in a loop. At the top of the loop where the plane is completely upside down, pilot feels no forces from the seat or the seat belt. So same as this, that's normal force is 0. If the plane speed is 120 meters per second, what's the radius of the loop? This is pretty much exactly the same problem as this. So we just have a different thing that's unknown. If you're just barely weightless at the top, that's the same as the normal force backing off to 0, which means it's only gravity toward the center of the circle. So mv squared over r is equal to the force of gravity is 10 times mass. And now, we did have the mass of the pilot, the 75, but even if I had put that in there, it's going to cancel out, so I didn't bother putting it in. We did not need to know that. What's the radius of the loop? So I know here, if I want to solve for radius, I could multiply that up to this side and then divide by 10 over here. So r is equal to v squared over 10. So the radius of the loop is 1,440 meters. Right? The plane's flying a big loop, about 1.5 kilometers radius. Okay, here's some space stuff. In a distant solar system with a sun of mass, this planet is discovered circling the sun every 439 days. That's period. Now the first thing is that we're going to need to do, first thing is to switch this from days to seconds. So the period here, if this is days, then I need to multiply by 60, 60, and 24 to get from, by 24 to get to from days to hours, by 60 to get to minutes, and then by 60 again to get to seconds. I've done this enough times, I happen to know that there's 86,400 seconds in a day. That's what you get when you do 60 times 24, 86,400. You don't have to memorize that, you can just do it. So if I do 439 days times there's 86,400 seconds in a day, That's about whatever that is. I'm going to call that 3.8 times 10 to the... And then if you don't want to mess with this, you could just go with your mode into scientific notation mode. And that's about 3.8 times 10 to the 7 seconds. Okay. How far is this planet from the center of its sun? One of the equations that you are going to have is the t squared is equal to 4 pi squared over gm times r cubed. And I think I know what this is, the t, and I know what this is, the m. So I should be able to solve for the r, right? So I'm going to try to do that. First I'm going to just solve for r cubed. I'm not going to try to do it all at once. Now when I move this fraction to the other side, everything's going to flip upside down. So I'm going to have t squared times the gm on the top, and then divided by 4 pi squared. So I'm going to go ahead and... You know what? I can do a cube root at the same time as that, right? Because I got a fancy calculator. So I want the cube root of all this. And I want to make sure that I've got my g stored in there. I do, in my calculator. So this is how I'm going to get that all in there in one nice, neat calculation. Go to Math, get my cube root right there, and then I'm going to go into F1 to get my fraction, right? That's alpha F1 to get that. And then I'm going to put the period squared. The period was 3.8 times 10 to the 7th. I want to square that. All right, that's my period squared. And then I need to multiply by g. And then I need to multiply by the mass of this sun, which is 5.5 times 10 to the 30th. Got to be so careful entering this stuff. Very easy to mess it up. So that's the top of that, and then on the bottom I just have 4 pi squared. That's it. I mean, that's the nicest way to do it, right? It looks just like that. So that gives me let's call it 2.4 times 10 to the 11th meters. All right, and that's an answer that makes sense. This is how far is it from the sun for us compared to for us from the sun. We are 1.5 times 10 to the 11th meters. So this is like, I don't know, getting close to twice as far. And this was like similar sun to ours. Our sun is 2 times 10 to the 30th, and similar period. Of course, we go around in 365 days. So it makes sense that we would get an answer kind of similar to our planet. All right, number 8. Our sun has a mass of this. You can just use 2 times 10 to the 30th is fine. Based on the assumption that the Earth goes around the sun once every 365 days, calculate the distance from the center. Well, I just gave away what the answer should be there. So this is the same calculation as this, right? R is equal to the cube root t squared times gm over 4 pi squared. I wonder if I can just kind of fix this up. So let's see if we can find what is the period here for us in seconds. Well, for us, it would be 365 days times that 86,400. So for us, it's about 3.15 times 10 to the 7th. So let's see if I can go and grab this entry. If I go second, you know how to do this with your calculator, second entry, and then if that's not the one and you want to go back further, do it again, second entry, and then it brings this up. Except I can go back in here and edit stuff. So here, I want this to be like 3.15, or I'll change that to 3.2. oops, 3.2 times 10 to the 7th. And then our sun is just 2. Then delete, 2 times 10 to the 30th. And that, I fixed it up, so now that should give us something that will round to that. There it is, 1.5 times 10 to the 11th meters for us. And how about the speed at which the Earth circles the Sun? One of the other equations you're going to have is this. So here that's g, well, I don't need to write that out again, do I? I can just do it on my calculator. So the square root of, I want a fraction, and on the top I want to put g times m. The m is the mass of the thing in the center. That's the mass of our sun. 2 times 10 to the 30th over r, which we just found in part A. 1.5 times 10 to the 11th. That's the square root of g m over r. And that's about 30,000 meters per second. I'm not going to fuss at you about how you round that. Just please don't write down all of the numbers. Not appropriate to do that. All right. Communications company needs to put up a satellite into orbit that'll circle the Earth once every 24 hours. Why would you want to do that? Because then the satellite, if the satellite is going around the Earth at the exact same angular speed that the Earth is rotating, in other words, if they both go around once every 24 hours, then the satellite is always at the same point in the sky. So that's why you can put up a satellite dish, point it at the sky, and the satellite's always in the same place because it's in what's called a geosynchronous orbit. So where is geosynchronous orbit? How far up does it have to be? Here's some information here. That would be this same calculation again to figure out what the r is. And when I find that r, that is this distance. So if I want to know altitude, I'd have to subtract off the radius. This is altitude, like from the Earth up to here. I'm going to have to subtract off the radius of the Earth at the end. If this question was on the test and you forgot to do that, that'd be like a 1 or 2 points max deduction for forgetting to do that. So don't stress about that. Okay, so I want 24 hours. That's the period that I need here. And 24 hours times 60 minutes times 60 seconds. That's that number of seconds in a day again, right? 86,400. And what else do I need? Gee, there's the mass of the Earth. That's it. That's what I need to find the radius. So let me get all that entered in. So I want the cube root of fraction g mass of, oops, is the g, oh, let me do it in the same order here. Not that it matters, because multiplication you can do whatever order you want. The t squared, let me do that first, 86,400 squared times g times the mass of the Earth, which you were given here, 5.97 times 10 to the 24th. You can use 6 times 10 to the 24th. That's close enough. You could use that too. That's fine. And on the bottom, I need 4 pi squared. 4 pi squared. Right? That is call that 4.2 times 10 to the 7th meters. But I want the altitude, so the altitude is that minus the radius of the Earth. So this altitude, this is like way, way, way above where we put like space shuttles and international space stations. This is not low Earth orbit. So that's that number minus 6.4 times 10 to the 6. That's about 3.6 times 10 to the 7th meters. That is where you put a satellite if you want it to be like that kind of satellite that is always over the same place, in geosynchronous orbit. Geo means Earth, synchronous means same time, so same time as the Earth, geosynchronous orbit.